All right, in this video we're going to look at how to solve exponential equations. And there's basically two main ways to solve exponential equations. One way is by changing the base. The second way is using logarithms. And so this video is going to focus on changing the base to solve exponential equations. In class, we'll focus on using logarithms to solve exponential equations. So I'm just going to go through a few examples. First example, we're going to solve the equation 1/5 to the negative 2x plus 2 equals 25 to the 3x. So first thing, I don't know where, oh, there it is. First thing, you're going to be using this little chart. I will not give you this chart in a testing situation or a quizzing situation. This is merely for your convenience. So what you'll notice is as we do several of these problems, you'll start to get more familiar with some of these numbers and memorize them. If you don't get familiar with them, they need to end up on your cheat sheet. All right, so what we do is we look for these bases and we want to see which column both of those bases show up. So if I look here, this is the 2's column, 3's, 4's, 5's, 6's, 7's. If I look for 1/5 and for 25, I can see it right here and I can see it right here. So we're in the 5's column. So 1/5 is going to be rewritten as 5 to the negative 1. 25 is going to be rewritten as 5 to the 2. So I'm going to have 5 to the negative 1 to the negative 2x plus 2, and then 5 to the 2 to the 3x. So I haven't changed anything about what the equation represents or what it equals or any of that. I've just changed the form of some of the numbers. So everything is still equivalent. So now I just need to do what I know about exponents, which is if you have an exponent raised to another exponent, then they need to multiply together. And so on this side, I have 5 to the 6x. On this side, I have to be a little bit more careful because I'm multiplying a negative 1 by two different terms, and so that means I need to distribute that negative 1. So that gives me 2x minus 2. At this point, I can say that if the bases are the same, then I know the exponents have to be the same as well. And so I'm going to say I'm going to get rid of the base on each side. So I have 2x minus 2 equals 6x, and I'll subtract 2 over, so 4x. And then I'll go ahead and divide by 4, and I get negative 2 over 4 equals x, and negative 2 over 4 is the same thing as negative 1/2. All right, so a good way to check your answers is to grab a calculator, and then what I like to do is type in my answer and store it as x, and then what you can do is you can just type in the problem, exactly the way it looks, so the left side and the right side, and just make sure they equal the same thing. And so I got the same thing, that means that I checked my answer and it's good. All right, let's try another one. So for this one, we have 81 to the b minus 2 equals 243 to the negative 2b minus 3. And so I'm going to look at my chart and see where 81 and 243 show up in the same column, and I can see them both right here, 3 to the 4th and 3 to the 5th. So 81 is going to turn into 3 to the 4th. 243 is going to turn into 3 to the 5th. And then I'm going to go ahead and use my property of exponents, so I know that I'm multiplying these exponents together. So I have 3 to the 4b minus 8, 3 to the negative 10b minus 15, The most common mistake that I see here is a student who would multiply the 5 times the negative 2b, but not completely distribute, and they would miss the second part, and then their final answer is wrong. So either be really good about distributing or always check your answer. So the 3's cancel because they're the same now. So 4b minus 8 equals negative 10b minus 15. I can add the 10b to the other side. I can add the 8 over to the other side. And then I'll go ahead and divide by 14. Now the funny thing is, I didn't mean for these to have the same answer. But they do. So I'm going to go ahead and type this in again. So negative 1/2, I'll store that as b. And so I've got 81 to the b minus 2. Yep. And 243 to the negative 2b minus 3. And funky answers, but they're the same, so we got it. Okay. What I want to do next is try some problems using some other rules of exponents or properties of exponents that students are likely to have forgotten that can make these problems a little bit tricky. Okay, so here, instead of just having a left side and a right side with just 2 different bases, we actually have 3 different bases. So same thing, I'm going to look for on the chart where I see these bases, so 16, 1/8, and 32. And 16 is here, 1/8 is here, 32 is here, so it looks like I'm going to have a base of 2. So 16 is 2 to the 4th. 1/8 is 2 to the negative 3rd. 32 is 2 to the 5th. And then I'm going to go ahead and use my exponent to an exponent. It means I multiply. So 2 to the 4v, 2 to the 3v plus 9, 2 to the 5. And then here is where I have to remember another rule of exponents to see what to do with these two. So you can write this side example if you need to, just to recall, because I think when you look at it like this, it does not feel clear what you should do next, but you guys have been doing problems like this for a long time. So let's say I had x to the 2nd times x to the 5th, and I wanted to know what those were. Most of you guys would be like, oh, that's x to the 7th, and you wouldn't think twice. So anytime your exponent or your base is the same, you just add your exponents together. So here we have bases that are the same. That means we're going to add those exponents together. So I'm going to have 2 to the 4v plus 3v plus 9 equals 2 to the 5th. All right, so it's a pretty easy step. It's just one that in this context maybe doesn't feel quite as straightforward. So I'll ditch the 2's. I've got 7v plus 9 equals 5. I'll go ahead and subtract the 9 over, so 7v equals negative 4, and divide the 7, and so v equals negative 4/7. And then I'll check my answers just like I did with the other ones. I don't always check my answers for problems, but here I feel like it's so easy you might as well. Okay. So I've got 16 to the v times 1/8 to the negative v minus 3. That's the left side of the equation, which was 32, and then the right side of the equation is just 32, nothing to plug in. So that one's good. Okay, and then one last example, again using one of the rules of exponents or properties of exponents. We've got 64 to the a minus 3 over 16 to the negative 2a equals 64 to the a. All right, so on the chart we're looking for where 64 and 16 show up in the same column, and this type of problem is a little bit unique, and that's because 16 and 64 show up in the 4's, and 16 and 64 also show up in the 2's, and so that means there are 2 different ways to do this problem, and it's up to you. You can use the 4s, you can use the 2s. You're going to get the right answer either way. So I'm going to go ahead and have us use the 4s since we already used the 2s column. And so 64 is 4 to the 3rd. 16 is 4 to the 2nd. And then 4 to the 3rd. So again, we're going to do that same exponent rule, an exponent multiplied by another one. So this is 4 to the 3a minus 9. 4 to the negative 4a. 4 to the 3a. Okay. So now we have to think about what exponent rule is used if you have an exponent on the top and the bottom. So again, we're going to do an example off to the side. Let's say I had x to the 5th over x to the 2nd. I would say, oh, that's x to the 3rd. And that's because 2 of the x's on the bottom cancel with 2 of the x's on the top, right? But the exponential rule that we're using, or the property we're using, is you can subtract them. 5 minus 2 is 3. So if we want to bring these to be one base instead of 2, I can say 4 to the 3a minus 9 minus negative 4a. So I can just subtract those exponents. So now I can say my 4's cancel. 3a minus minus makes a plus. So I have 7a minus 9 equals 3a. Sorry. I can subtract my 7a over to the other side. So I get negative 9 equals negative 4a. Then I can divide by negative 4, and I get positive 9/4 equals a. So just like before, I'm going to go ahead and check my answers. So I have 64 to the a minus 3 over 16 to the negative 2a. And I want to make sure that equals 64 to the a, and it does.